this into the world of reciprocal trig functions. And the further we go into learning these techniques of integration, the more you're going to realize that in a lot of cases it's a little bit of trial and error. So we have to kind of come to grips with that. So when I write things like, ask yourself, can I save a secant squared or a secant tangent? It's like, okay, cool. Now that I've asked myself, now what? Because you get to number 6, and you can save a secant and a tangent. So we can do this. But a case could be made that you could actually save a secant squared. So again, what I mean by saving is just write it as a separate factor. So secant x, tangent x, and then separately from that I would write tangent to the 4th. All right, so that's what I mean by saving the secant times tangent. Now, the issue that comes into play is like, well, what if I used the trig identity, like for example, this one, converted the tangent over into secant? Like, couldn't I have saved the secant squared? Yeah, but I won't know that until I try something. All right, so we get to this step here, and if it's an easy enough problem, I should be able to pick out the u. All right. The issue here is that it's not an easy enough problem, so I can't just say, all right, let u. I'll actually play it out. Let u be tangent of x, for example. Play it out either on paper or in your mind. The derivative of that would be du equals secant squared x dx. All right, so if I'm swapping out my tangent, then the derivative of that should allow me to cancel everything else. That's not going to do it. So then I gotta get creative here, because I know the u is not going to be secant times tangent, because that would involve product rule, and it's going to be a mess. So you kind of have a sense that that's probably not going to be it. So what I might try to do is reconceptualize this, write it again. I'm keeping my secant tangent. I'm going to write tangent to the 4th as tangent squared dx. The reason I'm doing that is so that I can actually use this rule, because a corollary to this rule is that tangent squared is equal to secant squared minus 1. All right, all I did was solve it for tangent squared. So secant x tangent x, still I'm leaving that alone, but now I'm replacing the tangent squared that's in the parentheses with a secant squared minus 1. Now, I'll say that this is a shot in the dark, only because, I try to put myself in your shoes, but that being said, when you do a problem often enough, you're just sort of guided right to the correct approach. But I'm trying to play this out as if I were in your position, I'm looking at a problem for the first time, and I'm trying to diagnose how to do it. All right, so first attempt didn't work. If you looked at, even the function in its original form before you saved anything, you might say, all right, let u equal tangent, no. Let u equal secant, no. So you try something else. You try saving a secant tangent. If this didn't work, if this substitution didn't work, then I'd go right back to scratch and say, okay, well, maybe I have to save a secant squared. All right, so it really is the second attempt or maybe even the third attempt in a trial and error approach that's really getting the job done. Right? It only seems like, like that. I don't even know. Like, it only seems like I know what I'm doing. Let's just put it that way. There was always a moment in time where I was in the same position, even as an experienced teacher, where I see a problem and I'm like, dang, I have no idea how to do this. All right. Well, let me try this. All right, that didn't work. Let me try that. That didn't work. Let me try that. Get it on the fourth attempt. It's really fun when that moment happens while I'm teaching a class. Those are the best. If you've ever had that moment as a student where you're like, I don't even know, does he even know how to do this? That happens sometimes. But the correct substitution is that u would be equal to secant. How do I know that? Because if I take the derivative of secant x tangent x. All right, and that's precisely what I need, because the u is going to make the secant go away, so this becomes u squared minus 1. Even though it's squared, it's not a big deal because it's a polynomial. This is going to help you cancel out that. So it isn't until that moment that I know that I'm doing it right. All right, but again, it's experience. When people say this course is hard, they're talking. I think they're talking about this problem. What's that? I screwed up.
Is the u supposed to be squared?
No, I wanted it to just be the u, the secant. I could go with secant squared, but if I do that, I have a derivative of 2 times secant x times secant x tangent x, because it would be chain rule. When you're dealing with trig functions that are raised to powers, sometimes the power is part of the u, but it's very rare, because there's always that hidden chain rule that happens when you're dealing with the power of a trig function, right? So go with just the, whatever the trig function is, itself not raised to a power. Try that.
Squared minus 1 squared.
Yeah. So then we're looking at, because again, we know this works because of this expression matching this expression. So that secant x tangent x is gone, so is the dx. It's replaced with the du. Instead of the secant being squared, it's now u being squared. And you might look at this as u substitution or something like that. It's not even that complicated. Boil it out and use the reverse of the power rule. So integral u to the 4th minus 2u squared plus 1 du. An antiderivative would be 1/5 u to the 5th minus 2/3 u to the 3rd plus u plus c, where u is secant. All right, so 1/5 secant to the 5th of x minus 2/3 secant to the 3rd of x plus secant x plus c. That's a good looking problem right there. I like that one. I like the next one better though. Because you can go in any number of different directions with the next one. This is one of those indicator questions where it's like, if I get this, I think I get it. You know, the previous one, it's like, you could actually luck into the right u. Here, you might need to know something. All right, so possibilities for u. I mean, I'll read it from left to right. Maybe I'll try letting u equal to tangent of 3x. Again, I want to stay away from the power because that's going to make a chain rule. It's already going to be a little bit of chain rule, but nothing too crazy.
Question about you.
Sure.
I heard somewhere that whatever is your u, whatever is left is supposed to be the derivative of that u, and that's how you can tell if you have the correct u. Does that sound familiar?
It should be a multiple or a factor of whatever the derivative is. So it may, whatever's left may not be specifically the derivative, but it should only be off by a multiple.
Oh, by a constant.
Exactly.
Okay.
If it's off by a variable, all bets are off. And I know where you heard that from. The guy who said it is incredibly brilliant.
Yes, yes.
So the derivative secant squared of 3x times 3 dx I'm going to rewrite that a little bit. Du equals 3 times secant squared of 3x dx. All right, so when you're trying to mentally reason this out, because again, you don't always, I mean, if you can play it out in your mind a little bit, that's always going to be for the best, because that's just time and energy, writing, erasing, things like that. But you say, well, if I take the derivative of tangent, what am I going to get? Secant squared. Well, that's the other part, so that's a good idea. If I take secant, I'm going to get secant tangent. That may work. There's a possibility that you might get it using both U designations, but not guaranteed. And, yeah, we want to get rid of that 3 because there is no constant multiplier of 3. So let me just divide both sides by 3. And so I can do my substitution. That's going to get replaced with a 1/3 du. So instead of tangent of 3x to the 4th power, it's u to the 4th power. And instead of secant squared of 3x times dx, it's really 1/3 du. So I'm going to write that as 1/3 u to the 4th du. So 1/15 u to the 5th plus c, with u being tangent of 3x. So tangent to the 5th of 3x plus c. With cosecants and cotangents, ask yourself, can I save a cosecant squared or a cosecant cotangent? And you may be wondering, why these particular things? That's because they're known derivatives, right? I know that the derivative of cotangent is negative cosecant squared x. So that's only a constant multiple away from being this. And the derivative of cosecant is negative cosecant times cotangent. Right? So these are things that I know are derivatives. So basically I'm taking something that is a known derivative and isolating it in the hopes that whatever's left will lead to some kind of u that'll work for me. All right. So I'm looking at the next one and kind of comparing it to the one before. I don't know why I scrolled. The one before. Oh, that title is killing me. Hold on. It's not even letting me overwrite it. Oh, it's a highlighter. That was stupid. All right. That was just going to bother me. I mean, it was bothering me. So then, in number 8, the question is the same as the last one. Well, which way do I go? And so take a stab at it. We have even powers, but the last one we had even powers. We were able to identify tangent in the last one as being the way to go. So let's see if maybe cotangent is the way to go here. So let u equal the cotangent of x. The derivative of that, the derivative of tangent is secant squared, so they're cofunctions, so negative cosecant squared x dx. All right, so close, but not quite good enough. All right, so let's take another shot. Let's try the u being cosecant. In that case, the du would be negative cosecant x cotangent x. So then it's like, well, if that's the case, yeah, I'll cancel some stuff, but I'm not going to be able to cancel it all. So then we get into this idea. One of these two things must be the way to go. So let's see which way is the way to go. Again, it's all diagnosis. We're performing triage here. So let me try to save a cosecant squared. All right, so now we're kind of at a crossroads. It's a question of, well, is this the right way to go? Did I make a wrong turn? I don't know. It's at this point that you're either going to meet with the success or not. And so you're going to carry out the approach to the next logical step and go from there, or you're going to scratch it all and try something else. So I look at this and say, this is the derivative I want. When I create my u, I want it to have a derivative of this, which means my u should be cotangent in some capacity. So I have the cotangent here, but this is not cotangent. So the question I would ask myself at this point is, can I make it a cotangent? Is there an identity that would allow me to change a cosecant into a cotangent? Well, as it turns out, there is. All right, cosecant squared is the same as 1 plus cotangent squared. All right, so cosecant squared 1 plus cotangent squared. Now, I think personally, just knowing cotangent, just knowing that there is a relationship is good enough. Because you could always create that relationship. I don't think it's worth the space on your index card. That's my personal opinion. You may completely disagree, and I respect that. I mean, out loud, I respect that. But if you know your basic Pythagorean identities, well, just the root one, the main one. It's like the foundation of all trigonometry. Like trig doesn't happen without this rule, right? I can create all the other ones if I divide everything by sine squared of x. I would get 1 plus cotangent squared x equals cosecant squared x. Just by dividing everything by the sine squared. I can do the same thing if I wanted to divide by cosine squared. Divide everything by cosine squared, you get tangent plus 1 equals secant squared. All right, so that's what I mean when I say that it's not worth the space on your index card, because if you know the basic one, you could always just create the other one. How often are you going to need this relationship that it's going to occupy valuable space on an index card? Not that often. All right. So now I can designate my u as cotangent. Du would be equal to negative cosecant squared x dx. I need a positive, so I'm going to negate both sides. Which is going to allow me to swap out this and this for this. Everywhere I have a cotangent, it's going to be replaced with a u. So 1 plus u squared. And yeah, you can substitute in multiple places. U to the 4th du. I'm going to slap a negative on in the front to account for the fact that it's a negative du. All right? Then I multiply. u to the fourth plus u to the sixth du, integrate 1/5 u to the fifth plus 1/7 u to the seventh plus c, and then reverse substitute with my known u, which is cotangent. So negative. Question? Why is the derivative of cotangent negative cosecant? Oh, because cofunctions have derivatives that are negative cofunctions. So it's always a co and a negate. And that's our antiderivative. We're going to talk